Hi. In last semester, we have studied the ordinary differential equation of first order and first degree. In this semester, our first topic of our syllabus is linear differential equation of nth order and its application. So let us start the topic. Linear differential equation. Linear differential equations with constant coefficients. Linear differential equations with constant coefficients and its applications. So first see what is meant by linear differential equation. So this is a differential equation which contains dependent variable and its derivatives occurs only in first degree, not multiplied together. It's called as a linear differential equation. So what is meant by linear differential equation with constant coefficient? So let us see the definition of linear differential equation. Linear differential equation with constant coefficients. So an equation of the type nth derivative of y with respect to x plus k1 into n minus 1 derivative of y with respect to x plus k2 into n minus 2th derivative of y with respect to x plus k3 into n minus 3 derivative of y with respect to x and so on. Last term is kn into y is equal to capital X. So say this is equation number 1. See once again, nth derivative of y with respect to x, where y is a dependent variable and x is independent variable. So express this equation in terms of x and y. So first term is nth derivative of y with respect to x. Second is k1 into n minus 1 the derivative of y with respect to x, k2 into n minus 2 the derivative of y with respect to x, like that. So on last term is kn into y is equal to capital X. So this is the general form of linear differential equation with constant coefficient. So where k1, k2, k3 and so on, kn are constants and capital X is the function of small x only. So this is the definition of linear differential equation with constant coefficients. This contains derivative terms constant k1, k2, k3 and this higher order derivative term is nth derivative. So therefore order of this differential equation is nth order differential equation. And in RHS there is capital X. This capital X denotes function of small x only. Okay. So in this topic we have to study how to solve this type of differential equation. So for that we have to define a new operator, call it as differential operator. So next definition is differential operator. Now here we have to define differential operator. So here we denote d by dx by capital D. That is, we have to define a notation capital D for d by dx. That means capital D indicates derivative of any function with respect to x. What is meant by capital D? Derivative of any type of function with respect to x. Similarly, second derivative with respect to x we denote it by d square. Similarly, third derivative with respect to x by d cube, etc. So we have to define this notation for simplicity of this equation number 1. So d by dx means capital D. Second derivative with respect to x means d square. Third derivative with respect to x means d cube. So this is the notation. Like that, fourth derivative with respect to x means d raised to 4, nth derivative with respect to x means d raised to n, like that. So using this notation in equation 1, we have to reduce this equation 1 in the form of here. So if we use the notation, that is differential operator, in equation 1, we can write the equation 1 as, that is nth derivative with respect to x means d raised to n into y as it is, plus k1 as it is, nth minus 1 the derivative with respect to x means d raised to n minus 1 into y as it is, plus k2 into d raised to n minus 2 into y, plus k3 into d raised to n minus 3 into y, plus last term is kn into y is equal to capital X. Now, using differential operator capital D, we have to reduce the equation 1 in this form. Now, if we observe this equation, there y is a common term. So, we have to take y as a common. So, this can be written as d raised to n plus k1 into d raised to n minus 2. Sorry, n minus 1 is here, plus k2 into d raised to n minus 2, plus k3 into d raised to n minus 3, and so on, plus last term is kn into bracket y is equal to capital X. So if you take y to be common, this above equation reduces to, in bracket, d raised to n plus k1 into d raised to n minus 1 plus k2 into d raised to n minus 2 plus k3 into d raised to n minus 3, like that. Kn into y is equal to capital X. Now, if we observe this equation, the bracketed term contains capital D only. So this can be write as function of D. This bracketed term we should have function of D into y is equal to capital X. Here this is equation number 2. So this is the another form of differential equation. This is in small d, this is in capital D. So see here, this is your another form, that is second form of given differential equation, and this is your first form of the differential equation of nth order. Now using differential operator, we have to reduce this differential equation into this form. Now we have to define auxiliary equation. Now see the definition of auxiliary equation. Auxiliary equation. So see here what is meant by auxiliary equation. In shortcut we call it as AE, auxiliary equation. So if f of capital D into y is equal to capital X is given differential equation, then the equation f of capital D equal to 0, that is only this term, we have to consider only this term, f of D equal to 0, we have to equate f of D equal to 0, is called as auxiliary equation. It's called as auxiliary equation. Now see once again, first we have to define linear differential equation. After that we will see the definition of linear differential equation with constant coefficients. After that we have to define a new operator, we can call it the differential operator capital D, that is equal to d by dx, and using this differential operator we have to reduce equation number 1 to the form f of D into y is equal to capital X. Now after that we have to define auxiliary equation. Auxiliary equation means what? If f of D into y is equal to capital X is your given differential equation, then we have to equate only f of D equal to 0. We have to equate only f of D, that is coefficient of y, equal to 0, and we call it as auxiliary equation. Now after that we have to define a solution of differential equation. Once we get a differential equation, then you know about the solution. So see here how to solve or how to find solutions of differential equation with constant coefficient. So first see the solution of linear differential equation. So the general solution, or complete, we say that it has complete solution. general or complete solution of given differential equation of given differential equation f of d into y is equal to 0 is, so general solution that is equal to complementary function. Here complementary function we denote it by CF, that is complementary function, plus particular integral we denote by PR. And in mathematical notation, this can be written as general solution, that is y, dependent variable y, is equal to complementary function we denoted by yc, plus particular integral we denoted by yp. So y is a dependent variable and yc is a complementary function and yp is a particular integral. Both are the contains independent variable x. So general form of solution of differential equation is y is equal to function of x. So after that, how to find complementary function, or what is meant by complementary function and what is meant by particular integral. So let us see the what is meant by complementary function and what is meant by particular integral. So see here, first definition of complementary function. Definition of complementary function. So let us define the complementary function, that is CF, complementary function. General solution contains complementary function and particular integral. So in definition, complementary function is a part of solution. So complementary function means it is a part of solution. Part of solution which contains number of arbitrary constants equal to the order of differential equation. See once again, definition of complementary function. It is a part of solution. That is, complementary function is a part of general solution of given differential equation which contains number of arbitrary constants equal to the order of differential equation. That is, if we have to provide a differential equation, then first see the order of given differential equation. If order is 2, then complementary function contains 2 constants. If order of differential equation is 3, then complementary function contains 3 constants. Like that. If order of differential equation is equal to the arbitrary constants contains in complementary function. Now after that, see what is meant by general solution. What is meant by particular integral. So see the definition of particular integral. So we denote it by PR. So see the definition again, same as above. It is a part of solution. It is a part of solution which satisfies the given differential equation. See the simple definition of particular integral. Particular integral means it is a part of solution, again same, part of solution which satisfies the given differential equation. That is, we have to find such a function. We have to find particular integral means we have to find such a function which satisfies the given differential equation. Now, question is that to find general solution of given differential equation, we have to find complementary function and plus particular integral, and we have to add together to write the complete solution. one by one we have to see the how to find complementary function and how to find particular integral. So let us see the first how to find complementary function or methods to find complementary functions. So there are four types of, there are four methods to find complementary function. There are four methods to find complementary function. So we have to see here one by one. So after that, methods to find CF, that is complementary function. Complementary function. So to find complementary function, we have to use auxiliary equation. How to find auxiliary equation? That is, in given differential equation, we have to use the differential operator capital D and reduce the given differential equation in the form of f of d into y is equal to capital X, and then we have to equate f of d to 0, we get auxiliary equation. And then this auxiliary equation is an algebraic equation, either it is quadratic, cubic or linear or fourth degree equation or fifth degree equation, like that. So we have to solve this algebraic equation or auxiliary equation and find out the roots. And according to nature of roots, we have to decide a methods to find complementary function. So there are four methods. So first one is, see here, if roots of auxiliary equation are real and distinct. That means if we solve the auxiliary equation f of d equal to 0 and find out the roots, and if we observe the roots, we observe that all roots are real and distinct, then how to write complementary function? See here. If r1, r2, r3, r4 and so on are the roots of auxiliary equation f of capital D equal to 0, such that all are real and distinct. See your first case. If you solve the auxiliary equation f of d equal to 0, this is algebraic equation. If this is quadratic, then we have to find out the roots. We have to factor. We have to prepare factor, or we have to use directly formula to find the roots of quadratic equation. And if this is cubic or fourth degree equation or fifth degree equation, then we have to use synthetic division method. So if we solve the this f of d equal to 0 equation and find out the roots, and roots are r1, r2, r3, r4, r5, like that. So once we get r1, r2, r3, r4, then we have to observe these roots. And once we observe the roots, we have to decide which one is real, which one is distinct. So if we get all the roots are real and distinct, then see how to write complementary function. Then CF is equal to, now CF means what? See the definition. CF means it is a part of solution which contains number of arbitrary constants equal to the order of differential equation. So we have to take the constants in complementary function equal to the order of differential equation. So let us take the first constant C1. C1 into e raised to r1x. R1 is the first root. Plus C2 into e raised to r2x. Plus C3 into e raised to r3x. Plus C4 into e raised to r4x. Plus so on. So like that we have to write the complementary function where roots of auxiliary equation are real and distinct. So C1, C2, C3, C4 are the constants, and R1, R2, R3, R4 are the roots of auxiliary equation, all are real and distinct. Then only we have to write this complementary function. Now second case, see here, second case is if roots of auxiliary equation are real and repeated. So see here, in second case, if we solve the auxiliary equation f of b equal to 0 and find out the roots, and we get roots are real, but two or more roots or one root is repeated. Repeated means there are more possibilities. Repeated two times, repeated three times, repeated four times. So like that, we have to study one by one. So suppose R1, R2, R3, R4, R5 like that are the roots of auxiliary equation in which R1 repeated twice. Then what happen about complementary function? See here, if R1, R2, R3, R4 and so on are the roots of auxiliary equation f of b equal to 0, in which R1 repeated twice. Here R1, R2, R3, R4 are the roots of auxiliary equation in which R1 is repeated twice. All are real because we have to see the case. The roots of auxiliary equation are real and repeated. So for that R1 is real and repeated twice. So if R1 repeated twice, then CF can be written as then complementary function is equal to, now R1 is repeated twice, that means R1 occurs two times. So therefore, corresponding to that, we have to write C1 plus C2, that is two constants, C1 and C2, e raised to R1, that is repeated root, into x, plus so on. If R2 is again repeated, then we have to write same, C1 plus C3 plus C4x into e raised to R2x. If R1, R2 is not repeated, then we have to write like that, same as a distinct case. So if R1 repeated two times, then we have to write complementary function as like that. Now, what happened if R1 repeated three times? See here, what happened when R1 repeated three times. So let us see the next. If R1 repeated three times, then complementary function is equal to, now R1 repeated three times means R1, three roots are same. So corresponding to that, we have to take three constants. So we have to write C1 plus C2x, x is independent variable, plus C3x square, next term, into e raised to repeated root, that is R1 into x, plus so on. If next root is also repeated, then we have to write again same as that case, and if distinct, then we have to write CF for distinct root. Now next, what happens if R1 repeated four times? Let us see. If R1 repeated four times, then CF is equal to C1 plus C2x plus C3x square plus next term is C4x cube e raised to repeated root into x plus so on. So like that, if R1 is real and repeated, then we have to write the complementary function as C1 plus C2x into e raised to R1 into x. If R2 repeated three times, then we have to write complementary function as C1 plus C2x plus C3x square into e raised to R1x. And if R1 repeated four times, then we have to write the complementary function as C1 plus C2x plus C3x square plus C4x cube into e raised to R1x. Now you tell me, if R1 repeated five times, then how to write complementary function? Same as above. See, here C1, C2, here C1, C2, C3, here C1, C2, C3, C4. Now, what happened if R1 repeated five times? Then complementary function is C1 plus C2x plus C3x square plus C4x cube plus C5x raised to 4 into e raised to R1x, like that. Now let us, this is the complementary function if the roots of auxiliary equation are real and distinct, real and repeated. So let us see the examples depending on this, and after that we see the next two cases of to find complementary function. So see the examples. First example is here. Solve second derivative of y with respect to x plus 5 into first derivative of y with respect to x plus 6 into y is equal to 0. So this is your given differential equation and we have to solve this differential equation to find complementary function. So this given differential equation in the form of equation number 1, that is in small d. So first we have to reduce this differential equation by using differential operator capital D in the form of f of capital D into y equal to 0. And after that we have to write the auxiliary equation, then solve the auxiliary equation and find out the roots. And after that we have to observe the roots and see the nature of roots. If roots are real and distinct, then we know how to write complementary function, and if roots are real and repeated, then also you know about the how to write complementary function. So see here solution. So given differential equation is second derivative of y with respect to x plus 5 into dy by dx plus 6 into y is equal to 0. Capital X is 0. So put differential operator d by dx is equal to capital D. So we can write above equation as capital D square into y plus 5 into capital dy plus 6 into y is equal to 0. Now see here y is a common, so this can be written as d square plus 5d plus 6 into y is equal to 0. Now this is in the form of f of d. This bracketed term is f of d, f of capital D into y equal to 0. So therefore the auxiliary equation is f of d equal to 0. F of d means what? This bracketed term. So we have to equate this bracketed term to 0. So therefore d square plus 5d plus 6 equal to 0. So this is your auxiliary equation. Now we have to solve this auxiliary equation. So if we observe this equation, let us see, this is quadratic equation in capital D. So we know how to solve quadratic equation and find out the roots. So this is quadratic, so this can be written as again d plus 3 and d plus 2. So these are the linear factors. 6, 3 2s are 6 and 3 plus 2 is 5 equal to 0. Therefore d plus 3 equal to 0 and d plus 2 equal to 0. So these are the linear factors. So therefore d is equal to minus 3 and d is equal to minus 2. So these are the roots of auxiliary equation. So observe the roots. Minus 3 and minus 2, these are the roots, two roots. So if we observe these roots, we get roots are real and distinct, not the same, different roots and real. So we have to use first case to write the complementary function if roots of auxiliary equation are real and distinct. So this is R1 and this is R2. So therefore roots of auxiliary equation are real and distinct. Therefore CF is equal to C1 into e raised to first root, that is minus 3 into x, plus C2 into e raised to second root, that is minus 2 into x. Okay, done. So this is your complementary function for the given differential equation. Do you understand? See, once again, we have to solve this differential equation. So given differential equation is second derivative of y with respect to x plus 5 into dy by dx plus 6 into y equal to 0. So this differential equation in the form of equation number 1. So we have to reduce this differential equation in the form of f of capital D into y equal to 0, and for that we have to use differential operator capital D, that is nothing but d by dx. So using this differential operator, after that y is a common term, so we have to take y to be outside. So this can be written as d square plus 5d plus 6 into y equal to 0. Now this is in the form of f of d into y equal to 0. So after that we have to write the auxiliary equation. So what is the auxiliary equation? This bracketed term is nothing but your auxiliary equation, and we have to equate this bracketed term to equal to 0 to prepare the auxiliary equation. So here we have to equate the f of capital D, that is nothing but bracketed term, to 0 to write the auxiliary equation. After that we have to solve this auxiliary equation, and this is quadratic, therefore we have to factorize this, or we have to use formula directly. If factorization is not possible, then we have to use formula. So see here, d plus 3 and d plus 2, these are the linear factors for this quadratic equation. So factoring this, we have to get the roots of d are minus 3 and minus 2. And if we observe these roots are real and distinct. And for that, to write complementary function, we have to use first case, that is roots of auxiliary equation are real and distinct. So that's why we have to write complementary function as c1 into e raised to first root, that is minus 3 into x, plus c2 into e raised to second root, that is minus 2 into x. So this is your complementary function. Now let us see the second example on d square plus 3d plus 2 into y is equal to 0. Now this is second differential equation given in the form of capital D, that is of the form f of this bracketed term is f of d into y is equal to 0. So we have to directly write here auxiliary equation. So in solution given differential equation is d square plus 3d plus 2 into y is equal to 0. So this is of the form f of d into y is equal to 0. So therefore the auxiliary equation is d square plus 3d plus 2 equal to 0. Now observe this auxiliary equation. This is quadratic equation in capital D. So factorizing this can be written as d plus 2 into d plus 1. So 2 into 1, that is 2, 2 plus 1 is 3. So these are the linear factors. So this can be written as d plus 2 equal to 0 or d plus 1 equal to 0. Therefore d is equal to minus 2 and d is equal to minus 1. These are the roots of auxiliary equation. So if we observe these roots, we know minus 2 and minus 1, both roots are real and distinct. So therefore roots are real and distinct. Therefore complementary function is, there are two roots, so we have to take two arbitrary constants. First one is c1 into first root, that is minus 2 into x, plus second constant is c2 into e raised to minus 1, that is second root, into x. So this is your required complementary function of given differential equation. Let us see one more example to find complementary function. So here, solve d cube minus d into y is equal to 0. So this is your given differential equation. So write down solution. The given differential equation is d cube minus d into y is equal to 0. So this is in the form f of d into y is equal to 0. So we have to directly write the auxiliary equation. So therefore the auxiliary equation is d cube minus d equal to 0. Now here d is a common, so this can be written as d into d square minus 1 is equal to 0. Now d as it is, this d square minus 1, this is of the form a square minus d square. So this can be written as d minus 1 into d plus 1. So that is equal to 0. Therefore, d equal to 0, d minus 1 equal to 0, d plus 1 equal to 0. So therefore, d equal to 0. From this factor we get d equal to 1, and from this factor we get d is equal to minus 1. So these are the roots of auxiliary equation. Now observe the roots. All roots are real and distinct. So corresponding complementary function can be written as roots are real and distinct. Therefore, complementary function is equal to c1 e raised to 0 into x plus c2 e raised to 1 into x plus c3 e raised to minus 1 into x. That is, cf is equal to c1 e raised to 0 is 1 plus c2 into e raised to x plus c3 into e raised to minus x. So this is your required complementary function for given differential equation. Now, if we observe all three examples, we observe that this 2 is the order of differential equation, this 3 is the order of this differential equation. So if 2 is the order of differential equation, then same as 2 is a degree of auxiliary equation. If 2 is a degree of auxiliary equation, then number of roots of auxiliary equation is also 2. And if number of roots are 2, then we have to take two constants in complementary function. Similarly here, 3 is the order of differential equation. Again, 3 is a degree of auxiliary equation. Therefore, we get 3 number of roots. Therefore, we have to take 3 constant, that is c1, c2, c3 to write complementary function. So, from that we can say that 4 equalities are here. First one is, so note down this, order of differential equation is equal to degree of auxiliary equation is equal to number of roots of auxiliary equation, that is equal to number of arbitrary constants in complementary function. So see here, order of differential equation is same as that of degree of auxiliary equation, it's same as number of roots of auxiliary equation, and that is equal to number of arbitrary constants involved in complementary function. If these 4 equalities are whole, then your complementary function is correct. Now let us see one more example to find complementary function. See, first example, solve d cube minus 5d square plus 8d minus 4 into y is equal to 0. So this is in again standard form, f of d into y is equal to 0. So we have to directly write the auxiliary equation. So in solution, given differential equation is d cube minus 5d square plus 8d minus 4 into y is equal to 0. So therefore, the auxiliary equation is this bracketed term equal to 0, we get auxiliary equation. So d cube minus 5d square plus 8d minus 4 equal to 0. This is your auxiliary equation. Now we have to solve this auxiliary equation, and if we see this, we get this auxiliary equation is cubic, and to solve cubic equation we use synthetic division method. So by synthetic division method, method. So by synthetic division method, we have to find first root by trial and error method. So see, if we put 1 here, so we get 1 minus 5, that is minus 4, and this minus 4 we get minus 8, and this plus 8 we get 0. That is, if we put d equal to 1, it satisfies this equation. That means 1 is the first root. So we have to write 1 is first root here, and here we have to write coefficients of all terms of d. So first coefficient is 1, second is minus 5, third is 8, and last one is minus 4. So we have to take vertical addition and take cross multiplication. So vertical addition 1 plus 0, that is 1, and cross multiplication 1 into 1, that is 1. Again vertical addition is minus 5 plus 1, that is minus 4, and cross multiplication minus 4 into 1, that is minus 3. Again vertical addition is 8 minus 3, sorry here minus 4 is here. Vertical addition 8 minus 4 is 4, and cross multiplication is 4. Vertical addition is 0. So therefore, as 1 is the first root, that means d minus 1 is the first factor, and second factor is from this d square minus 4d plus 4, and that is equal to 0. So this can be written as d minus 1, see d square minus 4d plus 4. This is perfect square. D minus 2 its square is equal to 0. So again this can be written as d minus 1 into d minus 2 into d minus 2 equal to 0. D minus 2 bracket square, that means multiplication of d minus 2 2 times, that is d minus 2 into d minus 2. So again, therefore d minus 1 equal to 0, d minus 2 equal to 0, d minus 2 equal to 0. So therefore d is equal to, from this we get 1, from this we get 2, and from this we get again 2. Now observe the roots. These are the roots of auxiliary equation. So observe the roots 1 to 2. So 1 is real and distinct, 2 is real but repeated 2 times. See carefully, 2 is a real root but repeated 2 times. So here we have to use first case real and distinct, and here we have to use second case real and repeated. So here roots are real and repeated. Therefore complementary function can be written as, now 1 is a real and distinct, so corresponding to that c1 e raised to 1 into x plus, now 2 is repeated 2 times. So 2 is repeated 2 times, so corresponding to that next constant is c2 plus c3x into e raised to repeated root into x. So this is your required complementary function. See carefully, 1 is a real and distinct, so corresponding to that we have to write only this term c1 into e raised to x by using first case of complementary function. Now second root is 2, but which is repeated 2 times, so corresponding to that we have to use second case, that is the roots are real and repeated twice. So therefore this can be written as c2 plus c3x, that is next constant, into e raised to repeated root into x. So this is your required complementary function. See another example. Solve d minus 1 bracket cube into y is equal to 0. This is simple example. Now if we see the differential equation, this is in the form of f of d into y equal to 0. So in solution, given differential equation is d minus 1 bracket cube into y is equal to 0. So directly we have to write the auxiliary equation is d minus 1 bracket cube equal to 0. D minus 1 bracket cube equal to 0. D minus 1 its cube, that means we have to take multiplication of d minus 1 3 times. So this can be written as d minus 1 and d minus 1 equal to 0. don't take cube root on both sides, because if we take cube root on both sides we get only one root, that is d minus 1 equal to 0, that means d equal to 1. But here, as if we solve this d minus 1 bracket cube we get here d cube. D cube means degree of auxiliary equation is 3. As the degree of auxiliary equation is 3, then we have to require 3 roots. So if we take cube root on both sides, we get only one root. That's why don't take the cube root on both sides. We have to split this d minus 1 bracket cube and like that, d minus 1 into d minus 1 into d minus 1, that is equal to 0. So therefore we get d minus 1 equal to 0, d minus 1 equal to 0, and d minus 1 equal to 0. Therefore we get d is equal to 1, 1, 1. So these are the 3 roots of given auxiliary equation. So if we observe these roots, we observe that 1 is a root which is real and repeated 3 times. Repeated 3 times. So therefore roots are real and repeated 3 times. So by using second case, so therefore complementary function is equal to, as 1 repeated 3 times, so corresponding to that we have to take 3 constants. So c1 plus c2x plus c3x square into e raised to repeated root, that is 1, into x. So this is your required complementary function. If roots repeated 3 times, then we have to write complementary function as like that.